Welcome to Ampersand, a new podcast series from Penn Arts and Sciences, where faculty from different disciplines discuss a topic they have in common. As part of this series, we're bringing you conversations with the new Dean of Arts and Sciences, Mark Trodden, who will be speaking with faculty from a range of disciplines about their research and topical issues in their fields of study. In this episode, Dean Trodden speaks with Bhuvnesh Jain, Walter H. and Leonore C. Annenberg Professor in the Natural Sciences, and the co-director of the Penn Data-Driven Discovery Initiative and the Penn Center for Particle Cosmology. The two discuss how advances in data science and artificial intelligence are transforming cosmology, teaching, and interdisciplinary research at Penn.
Well, welcome, Bhuv. It's great to be speaking with you. Thanks for spending time with us on the podcast. A lot of people don't know this necessarily because we've been here a while, but Bhuv, you're actually one of the reasons I came to Penn. You're one of the people that made me want to come here, so it's great to have you here. So we're both physicists. It's my first time talking to another physicist, and we both co-directed the Center for Particle Cosmology here at Penn. So certainly we could talk for hours. We could fill this entire time talking about dark energy or black holes. But I'd like to start out by asking sort of generally, how did you first become interested in this field? Why cosmology? And how did you get interested in the night sky?
Thanks, Mark. It's great to be talking with you in this setting. Indeed, we go back a ways, and I'm excited to be talking about cosmology and science in this setting now. I got interested in cosmology because the big questions of cosmology were fascinating to me. How did it all begin? What's this dark matter and now dark energy? Where's the universe headed? These were, always compelling from when I first encountered them. How it actually happened is a little more idiosyncratic, maybe. I got interested in basic physics questions. I think I was in 11th grade, and I was attending a family wedding in a small town in India. And you may know Indian weddings can go 2 or 3 days. And they're fascinating, full of music and dance, but I was not interested in those things as a teenager. And so I was holed up in my cousin's room, and it was full of these popular physics books. And I got really interested in these quantum mechanics questions. How can an electron be a particle and a wave? And I found Steven Weinberg's book, The First 3 Minutes, absolutely captivating. Looking back, I don't think I understood most of what I read at any depth at all, but that really stayed with me. And there were many twists and turns after that, but I think those were the moments when my, path got set.
Yeah, it's interesting. I'm kind of relieved to hear you say that. I think people often ask me, how did you become a cosmologist? And, they expect some origin story. I was a young boy, I looked at the night sky and I wondered. But really it's just, I was fascinated by little things, bits of physics, bits of mathematics, and just got into it that way. And only later do you find that path, I think, at least in my experience. In cosmology, certainly in the last, couple of decades, and certainly very recently, we've seen a big increase in the use of technology in general, I think, and therefore data. And I think the last couple of decades in particular have focused us very much on those topics. Could you just say a little bit about how that shift in cosmology has affected your own work?
Yes, it's a fascinating shift. It does seem like progress in astronomy in general has been led by data in the last few decades, with theorists doing plenty and generating great ideas, but the data is what is stimulating a lot of what's happening. I was trained in theory and simulations, so I came to data pretty late. I found data messy, really painful to deal with. There's so much you have to do before you can ask even the first question of a data set to clean it and format it. But I think for me, it was when I first appreciated that thanks to technology, our galaxy surveys are actually gathering a fair sample of the universe. In other words, in a year of observation, we're observing a representative sample of the entire observable universe. There's analogies with epidemiology that you want a good sample. So that realization was a bit mind-blowing to me. And then I just got excited that, yeah, we really can ask questions about a theoretical model of the entire universe that this data that has just come online can answer if we work right at it. So that's how I got into it. And then again, there have been twists and turns, and the latest big twist has been the use of AI in interrogating data. And that has been a new source of excitement.
We'll definitely get on to that. I think this question of the amount of the universe you're seeing is a big one. I think when I give public talks, I often say to people that, when my grandfather was born, we did not yet know that the smudges that you see on the sky were actually other galaxies. And now, as you say, in 2 generations, we're seeing, an appreciable fraction of the observable universe through our telescopes. That's remarkable. I know of no other field really with that sort of explosion, although I'm sure many people will correct me once they hear this.
That is really a great point. From going from trying to decide whether this smudge is nearby in our galaxy or an external galaxy to now you take a 1-minute exposure and you see a 90% across the observable universe. That still blows my mind.
It's incredible. So, as you say, it's a massive change in perspective, really, on how we think about the universe. How do you convey this to students? I know you spend a lot of time with both graduate students and undergraduates. I see them all over our offices. How do you teach them not just to compile the data, not just how to take it in from our instruments, but interpret it? Are there new tools or approaches that have transformed how you teach or conduct research in that way?
In astronomy, we have this luxury of all the beauty that's involved in doing astronomy. So I encourage every student to actually go to a telescope. In the last years, they were doing shifts in Chile at this really beautiful site. And to also just look at the pictures. I came from physics and math side myself. And so I was surprisingly slow to just enjoy the sheer beauty of these images in the process of extracting, statistical insights from them. So that's one thing I try to convey just through my own example. I don't have any deep insights or wisdom in getting students to do research. Lately, it's often a genuine partnership because the students are really at the frontier of data science and AI. So often they bring a new methodology that they've seen in the literature, and then we discuss whether it applies to our astronomical data set and the questions we're interested in. And then we jointly figure out how to adapt it and test it for our data, and then compare it to the old way of doing things and seeing if we are learning something different. So that's one example of how we are collectively, a few students and me, sitting and trying out new methods.
Yeah, well, I think that brings us to one of the big questions I really wanted to ask you, which is, about AI and its applicability and such things. So, obviously you've seen AI help you in your own research efforts. I know that. But maybe you could say a little bit about where that's been, most effective in your own research, and what do you see as its potential? And to ask the sort of big questions about AI, really, what are the limits or drawbacks of AI in terms of what it can do and how it's affecting science, as well as how students engage with research? I can imagine that, it gets them very excited to use these new techniques, but is there a cost to that? Like, what are they missing? How do you navigate that?
Well, Mark, how many hours do you have? There's a lot to unpack around AI. And, to be honest, everybody is just wrapping their heads around it. So what I'm going to say is just my own point of view, needless to say. And there's many other good answers. In astrophysics, AI enters in many small ways, for sure. It's, sped up or improved or provided an alternative to doing things like compressing data. We observe 1 billion pixels on the sky. We have just 4 questions to ask it. So AI provides this intermediate step of compressing that data to maybe 100 numbers. And the methods are not too dissimilar to how images are compressed when you want to send one over a WhatsApp message. I guess the other thing I'll say about AI in astrophysics is that we have another way of doing things. in many branches of physics, we have ways to reduce the raw data to something nicer. We have ways to use statistical approaches to interrogate the data. And we have a mathematical framework in which we can assess the answer. So that makes AI different from some fields where it's the first time that you're going to be able to do something like protein folding was a massive AI breakthrough because the other methods were just falling way short. For us, it's a little different because the other methods are providing us a reasonably good answer. So the advantage of that is that we can check AI. AI is famously difficult to interpret. It's a black box. So we have one way of checking it because we can do things using what physicists would call a more rigorous method. But AI is starting to provide answers that we couldn't get the other way. And that's a very exciting and uncomfortable moment. So sometimes it's the sheer volume of data. Sometimes it's certain calculations that it sped up. And sometimes it's this end-to-end framework it provides. It's called simulation-based inference, where rather than massaging the maps and extracting some clever numbers, you just compare a map of the universe to a map generated from a simulation of the theory. And that exercise is a little bit like looking at a picture of a cat and saying, is it an orange tabby or a calico or something else? Is this universe dark energy dominated or Einstein's gravity or some other theory? So that's a powerful and, like I said, deeply uncomfortable moment because physicists really want to know why you got that answer. And I'll just wrap up this part by saying that in the process of understanding how we got that answer, we are making contact with all the questions people are asking of AI. Why does ChatGPT hallucinate when you ask this question and give you the right answer for 99 other questions? So this question of interpreting and understanding how AI works is something that is very challenging, and sciences like astrophysics are providing a new way to examine it that I hope will help the broader question of interpreting AI. So I'm really excited about that possibility.
So we're mostly audio here, so people listening to us couldn't see the fact that when you said rigorous, you give air quotes around it a moment ago. So I want to explore that a little bit. I mean, I could imagine that when you say our physicists would consider these other techniques more rigorous. I mean, one thing you might just mean, which makes a lot of sense to me, is we understand them. We understand them end to end, and therefore we have a lot of insight into why that's the correct answer, which that would make a lot of sense to me. But another thing I could imagine you're wondering, someone might say, well, okay, I have a black box. I don't know how it got the answer, but I have an extremely good rigorous handle on what the error bars around that answer are. Is there any sense in which we have that with AI? You know what I mean? Like, we don't know how we got to this answer, but we do know it's right within these percentages.
That's a great question. You're on to one of maybe the most important piece of using AI for science, that how do you estimate uncertainty around your answer? And here the story is a little more nuanced than, say, for large language models. We do have ways of estimating uncertainty. And one way that we do it is that with AI, you can repeat the experiment over and over, and your answer is generally subtly different. And so by assembling all these different answers, you can make like a contour map around your right answer, and that is your estimate of uncertainty. You then have to check that the uncertainty estimate itself is not too uncertain. So that's a little complicated, but that's where the frontier is, checking the reliability of the uncertainty estimate.
So I guess with the risk of getting too much into the weeds here, because I'm just fascinated by this question, you run this model many times, let's say, and then you see how far away from what the range of answers is, and that gives you a measure of your uncertainty. But how do you have any that's one thing. But how do you know that the central point or anything like that is in fact the right answer? Do you know what I mean? You could have a very, very tight set of error bars around an answer that is fundamentally wrong. How do you get a handle on that?
Yep, that's indeed the other big question. And there I'm more worried, to be honest, because that gets at the traditional scientific process of checking every step of your calculation. And with AI, that's much harder. As you know, a neural net can have, millions of free numbers that we call parameters, and there's billions of calculations involved, and tracing back your answer is difficult. So in fact, to use AI for science, we are needing to develop new ways of developing what we call physical intuition and sanity checks. And some of it involves running the experiment many, many, many times and varying the input ingredients. So to pick a very concrete thing that we both work on, if you have dark energy and it's changing in time, then you make it change at different rates or increase and decrease. And you see how your answer shifts. And that's how you get an intuition for how the result responds to changes in the theory.
I see. That's fascinating. So, we've talked a little bit about your science and the role you're playing in astronomy at Penn and how AI touches that. Because of that interest and the way in which your research has gone, of course, you've been asked in recent years to co-direct the Penn Data-Driven Discovery Initiative in the School of Arts and Sciences, which is, one of our flagship efforts and was just launched in 2021. And the story behind that, I think, is particularly interesting. My understanding is you started a Zoom Hangout session during the summer of 2020 when we were all virtual and miserable. And it was people from all over the university, psychology majors attending lectures on astrophysics and criminology majors learning from biologists. And I know a lot of people in the Penn community are really excited about the growth of that program. How's it been going, and what do you see as the future of data science in the school and at Penn?
That moment when I first started what we call the Summer Undergraduate Data Science Hangout was a special one for me indeed. I personally felt that I was as excited about the possibility data science gave to talk to colleagues in different departments. It provides this language and it provides the tools that are common in physics, biology, and even political science. So across pretty much all of the arts and sciences, anybody doing empirically oriented research can have the shared language, and I really wanted to bring that to our students. And in some ways, undergrad students are bolder and more open to learning new things, and they don't know that if I'm a biology major, I'm not equipped to do a research project in astrophysics. If you just describe the problem, they're like, yes, this is using logistic regression, or this is using this kind of neural net. Let me give it a go. So the Data Science Hangout started that way, and it's been fascinating to see students teach each other and really enjoy the great presentations faculty from across arts and sciences give. We have started other programs in the Data-Driven Discovery Initiative, and it's been a lot of fun. We are trying to engage undergraduate, graduate, postdoctoral fellows and faculty, and so, all segments of arts and sciences. So we have this AI Fellows program that was, I think widely considered a big success of Data-Driven Discovery Initiative and is now becoming a university-wide program.
Yeah, that's been terrific.
Yes, I'm especially excited about it. It's this group of, worldwide experts in AI's applications in different fields. And they meet regularly and they talk to each other. And we've actually seen new collaborations launch between psychology, biology, computer science. On the other end, we have the Data Science for Social Good program, where we try to get a group of students to work with a professor on a problem that impacts the real world, whether it's Philadelphia or a distant coastal country impacted by global warming. And again, we are looking for genuine research problems where there's some data, some interesting question, but the students love the idea that while at Penn, they are working with the professor and producing answers that impact the real world. So this is a sampling of some of the exciting programs that we have.
Yeah, I have to say one of the most fun I've had recently, I came to a program you ran with 6 people from around the school giving talks in an afternoon. I stayed through the whole thing, even though I was only going to stay for one talk originally. And it was just great. I mean, just to see the range of applications of what's going on. So I can see where you are excited by this opportunity to interact with lots of different people. Of course, both of us teach physics in the School of Arts and Sciences, physics and astronomy. And, by the nature of the curriculum, all our college undergraduates take classes across the disciplines. So at some level, they, at least at the start, get the kind of breadth that you and I have been enjoying in various ways over the last few years. So that includes not just the natural sciences, but across the social sciences and the humanities. That's extremely different from my own university experience in the UK, for example. And I'm wondering, for STEM-oriented students in particular, what do you think is the benefit of this broad liberal arts education?
It's interesting you mentioned that your undergraduate experience was different. Mine was split because I did my first 2 years in Delhi University, and it was not very broad. And then I transferred to the US and was really excited to be able to take courses in philosophy and music. I barely passed that music course, by the way. So I have my own perspective on the value of a liberal arts education. Maybe I'll make this one very current comment about the value of liberal arts, which is that our education process, as you know, has been shaken up by AI, and the fact that some of the core mission of reading, writing, doing mathematical assignments is under threat by AI is maybe not too strong a way to put it. So in this context, we can ask, given the way AI is changing the world, what's the value of a liberal arts education now under this circumstance? And I truly believe that it's more valuable than ever for STEM students in particular to take courses in the humanities and social sciences. You can read in the newspapers and talk to people who will all say that honing a particular skill is, yes, valuable, but it's far from the only thing we bring to the real world. And we really need to bring the full cognitive package and preparation of being able to ask questions about what's interesting, of being able to critically examine answers that we are getting, of being able to imagine future possibilities. And I think that applies as much to research in the basic sciences as to any profession, journalism, law, finance, you take your pick. And so the only way we can get these skills is to have the broad liberal arts education that Penn offers. And I'll make one more comment about AI in particular, that if we take seriously the AI optimists or the AI doomers, then it's urgent to have some response to AI. And a humanities education, a liberal arts education, is what it takes to be able to answer, what does it mean to be human? What does it mean to have the right kind of impact in the world? What does it mean to grow intellectually or professionally? So I'm not saying that a liberal arts education automatically provides the answers. I think we do need to reimagine it and very practically work out some things afresh to be able to respond to this moment we are in. But this is the right place and the right kind of education to do it.
It's important that people know I didn't pay you to say that. I've been giving answers somewhat similar to that to many people as I go around talking not just about this moment in the school, but also the ways in which we're thinking about reimagining the undergraduate curriculum right now. And it's very much centered around these kinds of points, I would say. And yeah, I think it's a crucial argument that if you want to be able to thrive in a world that has the kind of uncertainty and questions that AI raises, that liberal arts education seems more important than ever to me too. We both went to grad school in physics, though, to do that. So if I were a young student thinking about going to grad school in physics, the world has changed a lot. What would you say to me today? And when you look back on your own career, what are you most proud of so far? I don't want to imply that it's over yet.
What to say to students starting graduate school is something I've been worrying about, to be honest. Students have a great deal of anxiety. Whether they're undergraduates or graduates, the world that awaits them when they leave Penn and look for jobs and find their place in the world. And I don't have great answers to alleviate that anxiety, because I do think the future trajectory of different professions is going to change. So the advice that I would give to a student is that, grappling with difficult questions in physics, as in any other discipline, is a thrill of its own. And graduate school is the time to experience that thrill. That struggling with learning and uncertainty is quite uncomfortable. And I think with every succeeding generation of students, it's a challenge for us to have them experience that discomfort and take the patience that it takes to make advances of their own at a time when things are moving so fast, when AI is available to help them along much faster. So I try to convey the value of sitting with your own thoughts and turning a problem over and trying many things, even though you know that at first they won't work. So those are some of the core skills. Of course, I love talking about what a thrill it is to do astrophysics and to get even modest answers to the big questions and to look at the data and turn it over. So that's something that has not changed. The last thing I'll say is that when students graduate, especially in my kind of cosmology, which is maybe a little different from the great theoretical work that you do, because for you it's much more mathematical. For me, there's math, but there's also coding and data and those kind of skills. So students are very aware that they can transfer those skills pretty readily from a basic research question in astrophysics to a question of how to improve a vision language model for industry and work in big tech, or to work in finance, which is also using machine learning and AI a lot now. So at that point, I simply encourage students to find their true calling and to have the confidence that they can pursue and succeed in whatever path they take. And I'm really heartened that in fact the boundaries are more porous and you can go back and forth more than you could even 5 or 10 years ago. So that, I think, is liberating.
I agree with that. And I think one thing that I've picked up from the last few years, I think, is that our students are remarkably marketable in many different areas. And they're not marketable because we've changed what we do in graduate school. We still teach them to have all the best skills that the best physicists in the world should have. It just happens that many of those skills and that way of thinking, as you said, that way of addressing problems has become ever more powerful for all kinds of other problems that people face in different areas. And that's really sort of a nice thing, I agree. They're remarkably successful. One of the things that happened over my career has been that, and I don't touch data the way that you do, but it's been that, we've gone from relatively small data sets that have told us wonderful but maybe somewhat simple things about the universe to enormous data sets that are messy, that have told us complicated things about the universe. And in particular, often we're putting together data sets from very, very different kinds of experiments and using them together to tell us what the new questions are. And you mentioned the fact that, AI has allowed us a new tool to deal with lots of things. This is precisely one of the things that AI has allowed us to address, these large data sets. So, you said that, my work is different to yours and that it's mathematical and your work is different. But of course, we have found many things to do together over the years. And in particular, we've both been interested in some of the fascinating questions that have been thrown up by analyzing these big data sets. So, I wondered, what's your take on some of the recent exciting open questions in cosmology that have been thrown up by precisely this, looking at these huge data sets?
Yes, this is a pretty exciting time in cosmology. And it's exciting partly because there's some level of confusion and uncertainty. And now I'm saying uncertainty not in the sense of uncertainty bounds on some measurement, but the uncertainty in our own minds about what the measurements mean. So, we've had these puzzles of dark energy and dark matter that are driving much of our research. And now we have this very unexpected twist that dark energy, according to some measurements, is evolving in time and evolving not in the way that makes sense to most of us. So its energy density is growing in time, which any simple theory more or less disallows. And so it means either that we are not interpreting the measurements correctly, or on the theory side, most likely that the universe is a little more complicated than we expected. And you and our colleague Justin Curry have, to my mind, one of the most exciting ideas to explain this puzzle, namely that dark energy and dark matter are coupled to each other, and they're not, as we've assumed for reasons of simplicity, just completely independent, isolated entities. There are other exciting ideas, including, that our universe may have extra dimensions that change gravity and make it different from Einstein's gravity. So I have only half a foot in this theoretical world, but I'm having a ball reading the new papers that come proposing these ideas at the same time as I'm scrutinizing the measurements to see where there might be a gap, where there might be a misinterpretation. So it is indeed a really exciting moment, and I honestly don't know which way it's going to shake out, but I'm pretty sure we'll learn quite a bit more in a few years. So very exciting time.
Yeah, I agree, and I think we've been having fun together working on this precisely because of the kinds of different approaches to these problems that we bring together at Penn. So that's been fun. So I'll finish with the big physics question then, in that case. So what aspect of the unknown, that's what I'm asking you about. not just physics, which aspect of the unknown do you hope will be revealed or discovered during our lifetimes? And you can interpret that any way you like.
I'm going to step away from cosmology and talk about something that I think animates a lot of humanity, and I'm part of that, which is, will we find signs of life on another planet? This is a professional interest, but more than that, a hobby of mine, because this field of astronomy is so far from ours. But I love reading about the new findings. And I was captivated by the story that played out this spring, where there was some very intriguing evidence for what we call biosignatures, molecules that in our planet are produced by small creatures living on the ocean surface. And so if it was the same origin on this other planet around another star, that would be a very exciting discovery. It didn't turn out that way. And I was really disappointed to read the follow-up observations this summer that showed that a more mundane explanation was likely the correct one. But with Webb and other telescopes, we now have the capability to detect these subtle signs of organic molecules that are associated with life. So I certainly wouldn't bet on an advanced technological civilization, but I think there's a very good chance we'll find signs of life on another planet, and that would be just incredibly exciting.
Yeah, I think that's a great answer. I mean, it's far away from what either of us does. It's close to what people we know well do. And it would just completely change what we think of ourselves as humans, as people. It would completely change what we think of our place in the universe. And as cosmologists, we're used to this, right? We used to think the Earth was the center of the solar system, and then we didn't. And then we thought that the solar system was the center of things, and it wasn't. And then we thought our galaxy was the center of things, and it wasn't. So this cosmology has been a story of finding that we're not in that special place. And this would be another step in that, to find a different kind of life on a different planet. So that would be great.
Indeed. Wouldn't it be exciting if everybody's obsessed with artificial intelligence and we find another kind of intelligence that's not artificial?
That would be great. Well, this has been wonderful. It's been fun for me to talk about some of the things that I spend the other half of my life doing, but also just to hear about what you're doing in AI and the Data-Driven Discovery Initiative. It's been great. Thanks for coming in and chatting.
Thanks, Mark. It's been a pleasure.
This concludes the 5th special episode of Ampersand, our new Omnia podcast series. Many thanks to Mark Trodden and Bhuvnesh Jain for today's discussion. We're taking a break for the remainder of the fall semester, and we'll be back with new episodes of Ampersand in the spring. The Omnia Podcast is a production of Penn Arts and Sciences. Subscribe to the Omnia Podcast by Penn Arts and Sciences on Apple Podcasts, or wherever you get your podcasts, to listen to new episodes from Ampersand and all of our podcast series.